Welcome to this explainer. Okay, let's jump straight in. I want you to grab your smartphone, or just picture it in your head for a second. Think about the absolutely massive volume of data your favorite apps, your social media, your games, your group chats are processing every single second. We're talking millions of images, text messages, and user profiles just flying around seamlessly. But, how does your phone actually keep all of that stuff organized without just completely freezing up? Well, it all comes down to a kind of hidden architecture right beneath the surface.
Think about it. How does your phone search a million contacts in literally 1 second? If a computer's processor tried to just dig through every single piece of data sequentially, like digging through a giant disorganized pile of laundry, it would just crash. Or, best case, you'd be staring at a loading screen for hours. No way! Without a specialized organizational toolkit, handling modern data is just flat out impossible. And that toolkit? That's exactly what we are going to unpack today.
So here is our roadmap for today. We'll start with the data problem, move into the building blocks, check out this straight line, explore the web, and wrap up with finding the right tool.
Starting off with Part 1, the data problem and the ultimate solution.
Okay, so what is a data structure? Basically, it's a logical way to organize, manage, and store data for efficient access and modification. Think of it like a really highly efficient real-world filing cabinet, but for software. You wouldn't just dump all your school papers into a huge cardboard box and expect to find your math homework in 3 seconds, right? You'd use folders, tabs, and alphabetized drawers. Data structures are essentially those folders and tabs for computer memory, making sure data can be stored and retrieved as fast as humanly possible.
So why do we actually need them? Well, even the fastest processors out there have speed limits. If an app has a million items, scanning them one by one slows the search process to a total crawl. Plus, picture a real-world scenario where thousands of users are hitting a web server at the exact same time, like when concert tickets drop for your favorite artist. Without data structures keeping that information perfectly organized, that massive flood of simultaneous requests would instantly crash the server.
Now, before we look at the structures themselves, let's bust some technical jargon. You'll hear the term ADT, which stands for Abstract Data Type. An ADT is simply a mathematical model or a logical description. It tells us what the data represents and the rules for it, like what data it holds, the valid operations we can do, and how to handle errors. Think of an ADT as the blueprint drawn up by an architect. It's just the rules. The data structure itself, that's the actual physical house built from those blueprints.
Let's move to Part 2, building blocks, specifically primitive versus non-primitive.
All right, let's look at our primitive data structures. These are the absolute basics provided by programming languages. You've got integers for whole numbers, floats for decimals, characters for single letters, and booleans for true or false values. The main takeaway for you here is that these primitive types hold just a single value in one specific location in the computer's memory. They're basically the individual bricks we use to build everything else.
On to Part 3, the straight line, also known as linear structures.
Before we go too deep, let's quickly contrast our two main non-primitive categories. On one side, we have the straight line approach, linear structures. Here, elements are arranged sequentially, with simple one-to-one connections. On the flip side, we have the web approach, non-linear structures. These are hierarchical, they're stored in random order, and they have complex many-to-many connections. We're going to focus on that straight line first.
So the most common linear structure you'll run into is the array. An array is a collection of similar data types stored sequentially in contiguous or touching memory locations. You access them using an index number, which actually starts at 0. Think of an array exactly like a fixed row of school lockers. They're all right next to each other, which is amazing for direct access. You can go straight to locker number 5. But it's terrible if you suddenly need more space than you originally planned for, right? You can't just magically insert a new locker into a solid brick wall. So you end up wasting memory if you don't use them all, and you run out of space entirely if you need more.
So how do we actually solve the array's problem? Enter the linked list. Instead of consecutive memory, a linked list uses scattered memory. How do they connect if they're scattered? Through a pointer. Every element, which we call a node, contains its data and the memory address of the next item. It's basically a clever scavenger hunt. You read the first clue, which points you to a random location for the second clue, and so on. This dynamic size completely solves the array's memory wasting problem, but there's a catch. You can't just jump instantly to the middle anymore. You have to follow the trail from the very beginning.
Okay, now we need to learn a really crucial acronym for our next linear structures, LIFO. It stands for last in, first out. This literally means the very last element added to the structure is the very first one to be removed. And that LIFO rule, that powers the stack. A stack only allows insertion and deletion from one single end, which we call the top. Think of it exactly like a physical pile of plates in a cafeteria. You can only put a new plate on the top, which in programming is called a push. And you can only remove a plate from the top, which is called a pop. If you try to push a plate onto a stack that's reached its max limit, you get an overflow. And if you try to pop a plate from an empty pile, you get an underflow.
So why does this matter to you? Well, stacks are literally everywhere. Every single time you hit the undo button on your computer to fix a typo, you are popping a saved state right off a stack. When a computer solves a maze and has to backtrack from a dead end, it's using a stack to remember its path. It's a super simple idea, but it has massive real-world power.
To set up our next structure, we need to contrast LIFO with FIFO, first in, first out. In this method, the first element added is the very first one to be processed and removed. FIFO is the rule behind queues. A queue is a linear list where elements are added at the rear and removed from the front. Let's anchor this abstract concept to physical reality. It is exactly like waiting in line for lunch. The first person in the line is the first person served. Computers use queues constantly. For example, when multiple documents are sent to a single printer, they just wait in a queue to be printed in the exact order they were received.
Moving on to part 4, the web, or nonlinear structures. Our first nonlinear structure is the tree. Unlike arrays or queues, trees are hierarchical. They feature a root node at the very top, which branches down into internal nodes and finally ends at leaf nodes at the very bottom. You can explain trees pretty easily using the relatable concept of a family tree. You've got grandparents at the root, children in the middle, and then grandchildren as the leaves. Because of this branching hierarchy, searching a tree for data is vastly quicker than sequentially scanning a straight line of a million items. Next up, we have graphs. A graph is basically the ultimate tool for mapping real-world entities. It's a network made of points called vertices, or nodes, connected by lines called edges. But here's the really cool part. Those edges actually describe the relationship. They can be undirected, meaning the relationship is mutual. They can be directed, meaning it's a one-way street. Or they can be weighted, meaning there's a specific value, like a cost or distance attached to that connection. Just look at how these are applied in the apps you use every single day. A connection on Facebook is an undirected graph. You're both mutually friends. An Instagram follow or a boss-employee relationship, that's a directed graph. It flows one way. And mapping apps use weighted graphs, where the vertices are cities and the edges are the distances or travel times between them. Computers track all of these massive relationships using structures like an adjacency matrix, which is basically a giant grid mapping out every single connection.
Finally, part 5, the right tool for the job.
All right, here are your core takeaways. First, data structures are the secret to organizing data efficiently. Second, there is no single best structure. Different features solve specific problems. You wouldn't use a queue for an undo button, right? And you definitely wouldn't use a stack for a printer line. Finally, as a programmer, matching the right tool to the right problem is absolutely critical. Establishing the right data structure is the very foundation of building fast, modern software. So, I'll leave you with this final thought. Next time you pull up Google Maps to find the fastest route, or you frantically hit undo to fix a massive typo, take a second to ask yourself, which data structure just saved your life? Because now you know the hidden programming architecture powering your everyday life. Thanks for joining me on this explainer, and keep exploring.